Good morning, students. This is class number 6 of Unit 3 in Group Theory Mathematics for the second BSc students who are studying third semester. Now, we are going to the theorem number 16. Previously, we have learned 15 theorems in this unit, Unit 3. This is class number 6 of this Unit 3. The statement of theorem number 16 is, if G is group, then prove that the center Z of G is normal subgroup of G. Here we observe that center Z is the new term in this unit. Is it right? Yes, I will explain in the proof what is center Z. Okay, right. For that, first of all, what is given in this theorem statement? Given G is group. What is that? G is group, and we have to prove center Z of that G is normal subgroup. We have to prove that this center Z is normal subgroup of G. Okay, right. For that, in the proof, I am writing that what is given, that is given that G is group, and this is called Z of G, that is center Z of G. Is it right? Here in the statement we have center Z of G. Is there? That is the symbol of this, like that. We can write the center Z of G is like that, Z of G. And what is that set is that contains the elements X which are in G, such that Ax is equal to Xa for all A belongs to G. Ax is equal to Xa for all A belongs to G. That means that element X is satisfying commutative law or abelian law with any element in G, with any element A in G. These type of element X collected in a set, that set is called Z of G, that is center Z of group G. Okay, right? Now we want to prove that the Z of G is a normal subgroup of G. That is simply you can say that Z is normal subgroup of G, center Z. For that, I am taking two elements, because if you observe that in the normal subgroup, we have, if any non-empty subset to become a normal subgroup, it must satisfy two conditions. What are they? The first condition is the subgroup condition, and the second condition is the normality. Is it right? For that, first of all, I will prove that the center Z is a subgroup. Next, second condition, center Z is a normal. Then we say that center Z is normal subgroup. Is it right? For that, I am first proving that center Z is a subgroup. For that, I am taking the two elements that x1 comma x2 belongs to Z. Students, kindly follow the cursor. Let x1 comma x2 belongs to Z implies, that means x1 satisfying abelian law with any element of G. I am taking an element A belongs to G. That means x1 satisfying abelian law with A. That means Ax1 is equal to x1A. That is x1A is equal to x1. And also x2 belongs to Z means x2 is satisfying abelian law with any element in G. What is that element? Any element is A. I am taking that A is an element. That means x2 is satisfying abelian law with A element A. That means Ax2 is equal to x2A. Okay, students, are you observing that? Right. Next, we have x2A is equal to Ax2. Is it right? Right. I am multiplying both sides with x2 inverse. The left side LHS part is multiplying with in the left side x2 inverse, and also right side with x2 inverse, and also on the RHS side also x2 inverse. x2A is multiplying with x2 inverse and x2 inverse, and now we are multiplying x2 inverse into x2. What happens x2 inverse into x2? Because x2 is also in Z, means Z is in G. That means x2 is also in G. What is the G? G is a group. G group means it is satisfying closure, associative, identity, and inverse laws. Is it right? By the inverse law, we can say that x2 inverse into x2. Students, kindly follow the cursor. x2 inverse into x2. What becomes? By inverse law, x2 inverse into x2 becomes E. E means identity. E into A means A. Okay, right? I am writing A. x2 inverse, right side x2 inverse is as it is. And the next one, x2 inverse into A is as it is. And what about x2 into x2 inverse? x2 into x2 inverse is E. E means identity. A into E is A. So what remains? In the LHS part, AX2 inverse. In the RHS part, X2 inverse into A. That means X2 inverse is satisfying abelian law with an element, any element in G. Is it right? That means that X2 inverse belongs to Z. We are taking X2 in Z. Their inverse X2 inverse is also in Z. Now, what about X1, X2 inverse into A? X1, X2 inverse into A. Okay, right. Now I am testing that X1, X2 inverse into A. I am writing by associating law X2 inverse into A in the same bracket and X1 is outside the bracket. Okay, right? Next. What about X2 inverse into A? What we got here? X2 inverse into A. X2 inverse into A. What happens? That is A X2 inverse. Is it right? I am replacing X2 inverse A with A X2 inverse and X1 is same. X1 is same and X2 inverse into A becomes A X2 inverse. Okay, right? Next, I am again using associative law for the three elements. That means I am interchanging the brackets for the first two elements X1A and the X2 is outside the bracket. Okay, right? Then what happens? A X1, X1A, we have here X1A is equal to AX1. Kindly follow the cursor. X1A is equal to AX1. I am replacing X1A with AX1. Again, I am writing associative law for the three elements. That means the interchanging of brackets. That is for the A is outside the bracket and the remaining X1, X2 inverse in the same bracket. Then what we got in the first one? X1, X2 inverse into A and the last one A into X1, X2 inverse. That means this X1, X2 inverse is satisfying abelian law with an element A in G. That means that X1, X2 inverse belongs to Z. Okay? That means we are taking X1, X2 belongs to Z and X1, X2 inverse belongs to Z. That means Z is said to be subgroup of G. This is the first condition in the normal subgroup which was proved. Now we are going to the next normality condition. That is, for that I am taking that A belongs to G and X is in Z. Then what happens? AX A inverse. I am testing that AX A inverse. What will becomes like that? Because if you observe that X belongs to Z, X belongs to Z means X is satisfying abelian law with an element in G. Is it right? That means what is the element in G? A. X is satisfying abelian law with A. That means XA is equal to AX. We can use this AX is equal to XA in this bit. AX A inverse. What will becomes AX? AX can be written as XA because X is in Z. In Z means in Z, X is in Z means X is satisfying abelian law with A in G. Is it right? That means AX can be written as XA. By associative law applying on these three elements, we can interchanging the brackets. The X is an outside the bracket and AA inverse in the brackets. Okay. What will becomes AA inverse? A in G. What is G? G is group. Group means it is satisfying closure, associative, identity, inverse. By using that inverse law, AA inverse becomes E. X into E becomes X because E is identity. What is X? Where is X? X is in Z. That means if you observe that AX A inverse means X is equal to X, that is in Z. That means AX A inverse belongs to Z. I am taking the A is in big set G and X is in Z. AX A inverse is in Z. That means Z is normal. Simply we say that Z is subgroup and Z is normal. So we say that Z is normal subgroup of G. Okay. What is Z? Z is a Z of G. That is center Z. Center Z of G is normal subgroup of G. Therefore, theorem was proved. Here, we can take a note. If G is abelian, then that center of Z is equal will becomes G. Is it right? Okay. Now we go to the problem number 1. Okay. Problem number 1. What is that? Show that H is equal to 1 comma minus 1 is normal subgroup of group of non-zero real numbers under multiplication. What is that? We want to prove that H is equal to 1 comma minus 1 is a normal subgroup of real number set which is a group under multiplication and having the non-zero elements. Non-zero real number set with respect to multiplication is a group. That means for real number set is denoted by R and non-zero means I am subtracting minus in singleton 0. That means R, in that R, there is no zero element. R is subtracting with 0. That means R has no zero element. That is, R is a real number set with non-zero elements. Given that we know that this is a group with respect to multiplication. We want to prove that this H is equal to 1 comma minus 1 is a normal subgroup. Clearly H is lies in R because these are the non-zero real numbers. Because H is in R minus 0. R minus 0 can be taken as G. So H is subset of G. We know that H is group under multiplication. H is group under multiplication. Now this is a group means H is group, G is group. H is a smaller group. That's why we say that H is subgroup of G. That means subgroup condition is over. We want to prove this H is normal subgroup. First we prove that H is subgroup. Next, normality condition. We want to prove the normality condition. That is, for X belongs to big set G and for some element 1 belongs to H. What about X1 X inverse? What becomes X1 X inverse? X into 1 X. X is inverse. E means 1. Is it right? X inverse is 1 by X. That is 1. Similarly, X into minus 1 into X inverse. Because X is in big set G, minus 1 is in H. X minus 1 X inverse. What happens? This will becomes X into minus 1 minus X. X inverse means 1 by X. X cancels, that is minus 1. In these both places, 1 is in H, minus 1 is also in H. That means X1 X inverse belongs to H. X minus 1 X inverse is also belongs to H. For these two elements, X1 X inverse, X minus 1 X inverse, both are in H. That means H is normal. H is normal. See, simply we can write it as a definition. In the place of 1 comma minus 1, we can replace with H, which is in capital H. X, small h, X inverse. H replaces 1 here, and if you follow the cursor, here is a X, H X inverse replaces, H replaces minus 1. Here, in the place of 1 and minus 1, I am placing X, H, X inverse, that is H. Small h replaces in the place of 1 and minus 1. X, H, X inverse belongs to H, where H belongs to H and X belongs to G. This means this is the condition of normality. Here H is a normal, and here we put that H is a group and which is subgroup of G. That is H is subgroup. That means H is normal subgroup of G. Okay, right? We go to the another problem. What is that? Show that H is equal to 1 comma minus 1 is normal subgroup of G. Here G is not a real number set. In the previous problem, we have taken that G is a real number set of non-zero vectors. Sorry, non-zero real numbers. G is a non-zero real number set. Here I am taking that G is 1 comma minus 1 comma I comma minus I, which is called fourth roots of unity. We can learn this problem in the group theory. Okay, if you have any doubts, you can go to the group theory and you can observe that in that group theory you will get the proof of this G is a group under multiplication. Here we are using that this is a group under multiplication, and we want to prove this H is equal to 1 comma minus 1 is normal subgroup. Also write the composition table for the quotient group G by H. He is asking that. Also we want to prove another one, that is composition table. We want to write the composition table for the quotient group G by H, which I will end in the earlier classes. For that, first in the problem, I prove that H is normal subgroup. For that, H is equal to, what is that, 1 comma minus 1, and G is equal to 1 minus 1 I minus I, which is a fourth roots of unity. This is called fourth roots of unity. Is a group under multiplication, right? Clearly H is in G. Is it right? 1 comma minus 1 are in G. Is it right? Yes. So we say that H is contained in G. Clearly H dot is a group, because 1 comma minus 1, the set 1 comma minus 1 is a group. H is group and G is group. H is subset of G. That means H is subgroup of G. The smaller group is said to be subgroup. Which is smaller group in these two? H is smaller group. That's why we say that H is subgroup of G. Is it right? Then what we want to prove? H is normal subgroup. We have proved only subgroup. Okay? We have proved only subgroup. Now we want to prove that normality. What is that normality condition? Now, one is the identity in H. Is it right? It is very clear in the multiplicative. In the multiplication, one is the identity element in the set H with respect to multiplication. Now 1 into H. What happens? Each and every element of H is multiplying with 1 on the left side. What is H? 1 comma minus 1. If multiplying 1 into 1, 1. 1 into minus 1, it becomes H again. What about minus 1 into H? Minus 1 into, what is H? 1 minus 1. If I am multiplying each and every element of this H with minus 1 on the left side, minus 1 into 1, that is minus 1, minus 1 into minus 1, plus 1, right? This is again h. In this set also 1 comma minus 1 are there. This is h. That means 1 into h is h, minus 1 into h is h. Is it right? What about IH? What is that? IH. That is I is multiplying on the left side on each for the each element of h. That means I into 1, that is 1. Sorry, I. I into minus 1, that is minus I. What about minus I into h? Minus I into 1, minus I. Minus I into minus 1, that is I. This is IH. That is IH is equal to minus IH. Is it right? IH is the same as minus IH. Now, here we got that 1H. 1H is equal to H. What is H? H is equal to minus 1H. That means 1H is equal to minus 1 into H. Is it right? Similarly, we prove that 1H is equal to H into 1. If we multiplying 1 with 1 is on right side with the elements of H, we got the same H. That means 1H is equal to H1. Similarly, minus 1 into H is equal to H into minus 1. IH is equal to HI. Minus IH is equal to H minus I. That means each left coset is a right coset. That is H is said to be H is normal subgroup of G. Is it right? We know that G by H is quotient group, because if G is group, H is normal subgroup, then we proven that in the theorem number, I think it is 13, G by H is quotient group. G by H is quotient group. Now I am writing that the composition table, which is the second question. What is that? Also write the composition table for the quotient group G by H. Is it right? For that I am writing the composition table. What is that composition table with respect to multiplication? Dot is the multiplication symbol. Okay, right? I am writing that H, IH, H, IH. Is it right? For that, H into H becomes, what happens H into H? If you are multiplying HH, that is H with H, that becomes H. You can multiply with H with H, and each element of H with each element of H. Then we got same H. H into IH, what becomes? Each element of H is multiplying with H, then it becomes IH. Similarly, IH is multiplying with H is called IH. IH is multiplying with IH gives H. Is it right? Yes. So the composition table is also given for this problem. Okay, students. Now there is a minimum time for we have to prove that many problems. You can saw the problem and note down it. I will post this in the WhatsApp group. Then you can ask me the doubt for this proof solution. You will try to solve this problem, and after that you can check it with this one, because it was already proven in the previous problem also. Okay, students. From this we can say that we are approximately completed the main, that is the total. I almost completed the theorems in the group, that is unit 3 groups in groups unit 3, and we will explain the problems in our direct classes, so that is in offline classes, which will be conducted in the next week. So students, all of you come to college regularly for learn the problems directly, and you can clear the doubts in the WhatsApp also for the previous explained theorems and problems. And many problems will be explained in the classrooms, and also many theorems, the important theorems will also be repeated and explained in the classes also. If you have any doubts, call me anytime, and that means anytime is in the college time, that is morning 9 to evening 5 p.m. So students, all the best for this unit 3 also, and the mid exams will be conducted in the last week of this month or in the first week of next month. So students, all of you try to write the notes and complete the notes, and also learn the subject thoroughly to write the examinations. That means with good knowledge. Thank you so much.